Okay. Hello everyone. This will be the last talk of the Learning Tomography 1 session, and will be given by Robert Salzmann on optimal fidelity estimation in continuous variable systems.
Thanks so much. Thanks everyone for being here. Yes, this is joint work with Omar, Fawzi, and Aadil Oufkir. And if you like the work, the preprint is on the archive already. Let me start. The talk is about fidelity estimation. So it's like a very simple setup. Imagine you're in an experiment. You try to produce a certain state, a pure target state rho, but your experiment might not work the way you want. So you actually prepare some state sigma, and you don't really know what it is. So what you try to do is you try to certify that you produce rho or something close to it. In our figure of merit, how do we measure that we are close to rho is the fidelity. Okay, so we try here to estimate the fidelity between rho and sigma from measuring a few copies of the state sigma. So a naive way to approach this is just to do full state tomography to fully learn the state sigma. But this requires d squared many copies of the state if d is the dimension of the system. And this is, of course, very, very costly. So if you're on an n-qubit system, this takes exponentially number of copies of sigma. Or if you're on an infinite dimensional space or for some continuous variable system, this even requires infinitely many copies. Okay? So what's our way out? Our way out is that we don't try to learn the full state, but only the fidelity. And we try to utilize the knowledge of rho, the target state we have. Okay, so actually, if you now look at this a bit closer, the task becomes completely trivial and easy if you allow every measurement. So for example, you could just do this measurement, this projective measurement, asking the question, am I in the state psi or not? Okay. And then this actually is possible. We can estimate the fidelity only with a constant number of copies, independent of the state psi or the dimension d. But then you can also say, okay, this is maybe too much to want, because like this measurement for many states of interest psi is completely not feasible. If this is like highly entangled, we can actually not perform this. So what we want to focus on here are functional representation of the states, which can be directly measured in practice. And this has been kind of looked at before in these works, which I cite down here. So let me kind of now go to these two setups we want to consider. One is a finite dimensional case, discrete variable systems. One is continuous variable systems. What kind of functional representation I want to consider? So for the discrete variable systems, I consider the characteristic function of a state. So this is very easily obtained. You just consider like any Pauli string over these n qubits, and then you look at the expectation value with respect to your state, and this is the characteristic function. Let me calculate, or let me give some properties of these states, of these functions. So the L infinity norm is uniformly bounded over all states. This is important, and furthermore, the L2 norm, if you correctly normalize this thing, is also uniformly bounded over all states. So putting this differently, this just means that the set of all characteristic functions, which I denote by this SP here, is included in this bigger set S max. S max is just the intersection of these two balls, an L infinity ball and an L2 ball, and this will become important later on, so I denoted this here. Okay, now how does this relate to fidelity estimation? So the fidelity you can just express as the overlap between two characteristic functions for a pure target state rho. Rho we know, and we know its characteristic function, but the characteristic function of sigma we need to measure. And we just do this by performing Pauli string measurements with binary measurement outcomes. And this is obviously feasible in practice, right? This is just like a product measurement. This is very, very easy. And then the objective is to estimate the fidelity using this formula by performing just a few Pauli string measurements on a few copies of the state sigma. And the minimal number of copies sigma you need in this task to perform this with accuracy epsilon and probability of failure being bounded by this delta. In the worst case over all possible states sigma, this is denoted by this n function here. And you denote this superscript p here to say that we are on the discrete variable setup, or what I also call the Pauli model of fidelity estimation. Okay. And now what is the other setup? The other setup is this continuous variable systems. So here I'm on an infinite dimensional space. This L2 over R is my Hilbert space. And the functional representation I'm interested in is the Wigner function. Okay. So for that, I need to write down a phase space variable. This is essentially just the linear combination between position and momentum variable. And the Wigner function is then given by like an expectation of another observable, which is this interesting looking displaced parity operator. So here on the very right, you see like the displacement, bosonic displacement operator, the alpha, and also the number operator appearing. If you're not too familiar with continuous variable systems, don't worry, it's just like some observable, and the Wigner function is the expectation value with respect to this. Again, I want to collect a few properties. So these are very interesting, these Wigner functions. They are quasi-probability distributions. So they normalize to 1 if you integrate over them like a probability distribution does. But they're not necessarily non-negative. They can have negative values. And they also have similarly LQ properties as the characteristic functions do have. So they're uniformly bounded in L infinity. And also, if you correctly normalize, they're uniformly bounded over all states in L2 norm. So similarly, if I now write the set of Wigner functions as this LW, they're again included in some wider set as max, which is the intersection of an L2 ball and an L infinity ball. Okay, interestingly, so Wigner functions, mathematically, they lie in all these LQ spaces from 2 to infinity, but they're not necessarily in any of the LQ spaces below. So there exist pure states rho such that the Wigner function is not in L1. And this is quite interesting because this L1 norm of a Wigner function, this measures non-classicality of a state and also often appears as a computational, and it's a measure of computational complexity. So this thing can actually be infinite, and it really measures, okay, where and how much is my Wigner function negative. Let me now connect this again to the fidelity estimation bit. Similarly as for characteristic functions, the fidelity can be expressed as this overlap between these two Wigner functions. The Wigner function of rho, I know. The Wigner function of sigma I can again estimate by performing certain measurements, which are these displaced parity measurements. They also have binary measurement outcomes. And then also, like, this thing is something people actually do in current experiments. So this is really possible. They call this Wigner tomography or something like that. So yeah, people are actually performing this. So this is a very realistic setup. We now, using these measurements, we try to estimate the fidelity using only a few number of copies of the state sigma. And again, I denote the sample complexity now with this W, which is again the minimal number of copies needed to estimate the fidelity with accuracy and probability of delta being this epsilon and delta respectively. So, okay, those are the two setups. This is kind of like all I want to say for the introduction. Want to kind of remember this again. So this is the continuous variable setup I mentioned. What I want is to determine the sample complexity in this Wigner model. For discrete variable systems, the characteristic function plays a role. And I again want to determine the sample complexity in this model. And I want to ask a few guiding questions which should lead through this talk. So many people have studied, especially the discrete variable systems setup, and they came up with like efficient schemes there, for example, for certain classes of states. So for example, for stabilizer states, this is like constant, the sample complexity in the Pauli model is constant in number of qubits. But we ask kind of like the lower bound question here. So are there states for which fidelity estimation is hard? Especially in the Wigner model, so this is like some infinite dimensional setup. Are there states for which the sample complexity can be arbitrarily large? And for the discrete variable setup, the Pauli model, are there states for which the sample complexity scales exponentially in the number of qubits? This is a question we might ask, and kind of a bit more precisely also, we try to determine the property of a state rho, which actually governs the hardness of this learning task. If you look at both of these setups side by side, they're very, very similar. So what we want to do is to treat them in a unified setup, in a unified fashion. So what I introduce here is a bit more abstract framework, which I call black box overlap estimation. Okay, so I have some measurable space omega here, some abstract measure mu, and some set of functions s, which again lies in the set s max, which appeared already twice here. This intersection of these two balls, one in L1, L2, and one in L infinity. And you can think of this as being just a set of Wigner functions for your first example, or the set of characteristic functions for your second example. Okay. Now I have like two agents in this game. One is the function f, to which I have full knowledge. So this plays the similar role as, for example, the Wigner function of rho. And I have another function g, which I don't know, but what I can do is I have so-called black box access. So I can pick like points lambda in my space omega. And to each of these points, I have like a random variable which I can access, which has binary measurement, binary outcomes, and an expectation value. It just gives back like the function g for the specific point lambda. My objective now is to estimate a fidelity type looking quantity, which is this overlap between these two functions, okay, from as few samples of this random variable y as possible. And then I can denote similarly sample complexity, which is the minimal numbers of samples needed. And this now depends on the target function f, which I have, okay, but also the set of functions s, which I choose. And to convince ourselves that this really generalizes both of these fidelity estimation tasks, okay, if you take like omega to be the set of complex numbers and your measure being a rescaled version of the Lebesgue measure, this is really just the Wigner model of fidelity estimation. And if you take as omega the set of all Pauli strings and as a measure a rescaled version of the counting measure, this is the fidelity estimation task in the Pauli model. So I first want to overview the results such that you know where I'm trying to head, and then I try to sketch out a few of the results in a bit more detail. So what we find is, for many instances of interest, a full characterization of these sample complexities in terms of the L1 norm of the target function, or some smooth variant of that, and I will kind of go into the details what the smooth variant means. So in particular, if we look at the fidelity estimation task for continuous variable systems and look at Fock states, there the sample complexity scales as the square of the L1 norm, so increases as the photon number goes up to infinity. And this answers one of our first questions already, namely that the sample complexity in the Wigner model can be arbitrarily large. Furthermore, for the discrete variable systems and H-random pure states over these n qubits, we can show that the sample complexity scales as exponentially the number of qubits, like 2 to the n, which also answers the second question. And for the remainder of the talk, because I don't have infinite time, I will focus on the first two talks, and from now on, don't talk about the discrete variable systems anymore. So okay, now let me get a bit deeper. I want to discuss this black box overlap estimation task. So again, what is our objective? We try to estimate this integral over these two functions f and g from as few samples of this random variable y lambda as possible. And the main guy which determines hardness of this learning task is the smooth L1 norm. Okay? So if I take my function f, which is an L2 function, I can define a smooth version of this L1 norm by looking at a epsilon ball with respect to L2 norm around my function and picking the smallest L1 norm I find there. So I look at all these L1 functions f tilde, and I pick the smallest L1 norm I find. This is a nice quantity. It is finite because like L1 and L2, if you intersect them, are dense in L2. And it also kind of gives you back the L1 norm, so it's really like a comparable measure. If you take the limit epsilon to 0, you have this nice continuity property that you recover back the L1 norm, and it's infinite, or this limit happens to be infinite if your function wasn't in L1 in the first place. Okay, so this is an interesting quantity because of the following theorem, because for the set of functions being the full set S max, which I now have shown you a couple of times, we can actually really characterize the sample complexity in a very nice fashion. So we get essentially matching upper and lower bounds. Okay? So what you find is that both the quantity which determines hardness here is the smooth L1 norm. It scales essentially like the square of it, 1 over the square of the accuracy parameter, and logarithmically in 1 over delta, the probability of failure which is allowed. Furthermore, what I want to point out, because the finiteness of the smooth L1 norm, we can achieve this task with finite numbers of samples always for fixed target function f. Okay. Now we want to move more to the physical picture to actually estimating the fidelity for continuous variable systems. So okay, what is the task here? We want to estimate the fidelity overlap between these two Wigner functions from as few samples, from as few copies of the sigma as possible. And we ask the question, okay, can we also characterize in a similar fashion the sample complexity here, which is a sample complexity also corresponding to this black box model, but now with the set of functions not being the full set S max, but the set of Wigner functions inserted here. What we would like to have is essentially an analog of the result which we've seen earlier. Okay, I just kind of copied the equation from the last slide. The upper bound, of course, is immediately good because the set of Wigner functions is a subset of this S max, right? So our upper bound, we actually just get a stronger upper bound for the sample complexity in the Wigner model. But the lower bound, for the same reason, does not work out because the set of Wigner functions is a proper subset. Okay, so like the lower bound we could achieve would just be lower, and it's actually also quite complicated subsets to characterize. So our way out is to generalize the result we've seen earlier slightly. So we don't just look at the set of functions being this full set S max, but we look at any subset S, and we find upper and lower bounds now for the corresponding sample complexity. The upper bound is exactly the same you've seen before. Okay, there was no problem with that, but the lower bound now looks a bit funky. It involves the L infinity norm or the inverse of some L infinity norm, where you have an outer optimization over all these functions G1 and G2, which have kind of sufficiently spread overlap with the function f. So you have like this condition that the overlap is greater than 2 epsilon. So it looks very, very different from the smoothed L1 norm. It's not really, you don't see like any L1 norm appearing here. Still, this is a lower bound, and let's try to see what we get out of that. So because the set of Wigner function is a subset, we can immediately plug this in and get as a corollary simply by rewriting all terms in the physical language, these upper and lower bounds for the sample complexity in these continuous variable systems. Okay, nothing has happened here. And I want to, before analyzing the lower bound, I want to give a few remarks about the upper bound. So what we find is because the smooth L1 norm is always finite, we get a finite sample complexity for this task for all fixed pure target state rho, even if the Wigner function of rho has actually infinite L1 norm. Okay, this is quite interesting. And furthermore, the energy, very different from like the torque Francesco just gave, is not the quantity which determines hardness here. So you could consider this by looking at a certain family of states. So you fix your some state rho, and then you just displace them in phase space. You just move them further and further out with these displacement operators. So this family rho alpha you consider has blowing up energy. But because the L1 norms are translation invariant, nothing happens to the upper bound in the sample complexity. So over this full family, the sample complexity actually stays finite. Okay? So the energy is not really determining the hardness in this task. And this is really precisely due to that we know what rho is and we know where it's located in phase space. Okay, but the lower bound was still a bit obscure. So let's try to make this a bit clearer by looking at an example. And the example are Fock states. And with that, I want to tackle the question of hardness in this fidelity estimation task. Namely, are there questions with arbitrarily high sample complexity? So these Fock states, okay, they are just the eigenstates of the number operator or the quantum harmonic oscillator, which you all remember from like quantum mechanics undergrad courses. Their Wigner functions can actually be analytically computed. So they are given in terms of Laguerre polynomials with some exponential decay on top. This is just like the Wigner function of the 4-photon Fock state. So they have like this interesting oscillations. One thing what I want to point out, because the L infinity norm plays like an important role here, they are always peaked around 0. So like at 0, all of these Fock states are constant, and so they don't decay. This L infinity norm does not decay as n goes to infinity. Nevertheless, the L infinity norm appears in this lower bound. So this is just what I've shown you on the last slide. So, okay, if you really stare at this does not give you much at first, but you could just play around and plug in like certain example states of the sigma 1 and sigma 2. And that I want to do. So if you take sigma 1, just be the original Fock state, sigma 2 be a Fock state with like 2 photons more. Here you find a nice decay of the L infinity norm, because if you plug in like known asymptotic formulas for Laguerre polynomials and play around with them, you can actually show that like the L infinity norm difference between these two Wigner functions decays as n goes to infinity. And you can be a bit more quantitative even and really characterize the scaling of this L infinity norm appearing in the lower bound. So it vanishes as 1 over n. This is really good because if you now compare this to the lower bound, you see a few lines up. There's the inverse happening, right? So we get the lower bound on the sample complexity from that, scaling as kind of n, the number of photons. And we can compare this to the scaling of the Wigner negativity of these Fock states, which you can also determine using asymptotic formulas for the Laguerre polynomials. They scale as the square root of n, and plugging both together, you find the full characterization of the sample complexity for these states. Perfect. And it's just given in terms of the Wigner function of the Fock states squared. So this is very easy to write down formula and really tells you what's going on for this fidelity estimation task. That's actually the last result I wanted to show you. So I now give like a brief outlook and a brief perspective of these results. So I mentioned already earlier that the L1 norm is an important measure of Wigner negativity. It happens to appear in many resource theory of quantum computation as a measure of non-classicality and also measures a computational complexity of states and gates. What we find here is a new operational interpretation of this L1 norm in terms of this fidelity estimation task, and also for the first time that this L1 norm appears as a lower bound on the cost of some information processing task. And now you can ask the questions, are there more connections between the hardness of learning and the non-classicality and computational complexity of states going beyond just fidelity estimation? So there might be something more deep here to explore, especially from like this lower bound perspective. And another very concrete task what you can do, so you've seen that in all of this talk, I only use binary information for each of the measurement, or like each measurement outcome was binary. But if I measure a full Pauli string, I obviously get like way more than the binary information. I get a full bit string of information. So what is the optimal scaling if I use this full bit string of information? What happens here? This is the last open question I wanted to state. And with that, I want to thank you for your attention and answer questions.
Thank you. Thanks for the nice talk. So going back to your discrete variable case, you mentioned one of your main results is that there could be states that estimating the fidelity is exponentially hard.
Yeah.
Can you just give us an intuitive example of it?
Random pure states.
And how to see that?
So yeah, okay. Oh, does this work? Nope. Essentially, okay.
I mean, for that, you basically don't even have an efficient classical description of the ideal state.
True. But still, what you can get is like, so the whole black box overlap estimation thing is nice because you can also plug in the Pauli or the discrete variable setup, right? So like this theorem actually also holds true for these characteristic functions. You have like this lower bound, you can there even simplify it a bit because you can just plug in as one of these function G, the maximally mixed state. So essentially what this lower bound tells you is just, it gets big if you find a function, a characteristic function, which has like very, very small L infinity norm. So like this is 1 over the L infinity norm squared then essentially. And these random pure states have like very, very low L infinity norm. So you can just pick like as your like state G to which against you want to test essentially this random pure states with some small noise. This has still very low L infinity norm because these random pure states are very spread over all Pauli strings. And then you get that this is very large.
All right, thanks.
Hi. Thanks for the very clear talk. So you gave these high occupation Fock states as an example that were hard to estimate the fidelity. But presumably one could, for example, certify that the state is close to this state. So do you have any intuition as to whether there are any states that are hard to even determine whether you're close, say 99% close?
So whether certification is also hard for these states, essentially.
Oh, really? Okay.
No, that was the question.
Yeah, no, well,
I would presume so, yes. I can, like my intuition says yes, but I cannot really.
Even if you just measure the photon number and you just see it, it's always.
Okay, like okay, it always depends on the measurement scheme which you allow.
Right? I see.
Like this is also like was this very first thing. So it's really model dependent.
Ah, okay, right.
Because otherwise, what you could just do, like even fidelity estimation, you could just do, oopsie, that measurement like this psi versus 1 minus psi measurement. And there, like you could do this for the like exactly what you said, measure the photon number and it's constant. But measuring photon number is like very, very hard. So I kind of constrained to like these displaced parity measurements here.
Okay,
Thanks for the question.
Okay, I have a question.
Yeah.
So in the continuous case, suppose the energy is bounded, so does so in that case is the upper bound finite?
What was it? If the
Suppose the energy is bounded, so it's kind of establish a finite upper bound for this complexity.
I was thinking about this too because this was my original intuition that okay, we have some energy constraint and then we get an upper bound. The energy constraint which I was coming up then was a bit strange because it an energy constraint in terms of Wigner function just means that the first or then the second moment of the Wigner function is finite, and I needed another square in this Wigner function to make the result work. So it's not really an energy constraint. And then I was thinking a lot about whether finite energy implies finite L1 norm. And I was also talking to a few people, and actually I believe that this is true, but I could not really show this. So the answer is maybe.
Okay, another question is in the discrete case. So does your lower bound depend on the assumption that you only consider boundary measurements, but in practice, in poly measurements, actually you get many outcomes.
Yeah.
So suppose you utilize all this information, can you get better results?
I mean, this is exactly the intuition. So already for fidelity estimation, I know, but this is not really good. You get a square root speed up, which you can prove. I think this is like far from optimal, but there is like this important result was like in Robert's tutorial on Saturday and also last year's QIP talk on certification, which is like a slightly weaker task. And there they found that for almost all pure states, you don't need exponential number of qubits, but it's like n squared, I think, is sufficient. So like for using this full bit string of information, you get like essentially an exponential improvement over the sample complexity.
Okay, thanks.
Yes.
Yeah. Sorry, over here.
Yeah.
Yeah. So there are recent results on purity estimation with like single copy measurements that seem related to your work. I'm wondering if you can recover them by, supposing that rho and sigma are equal, and then whether or not you've thought about this connection to purity estimation, or if your results imply anything about them.
Not yet, but I would be very interested to discuss about this maybe in the break.
Yeah, we can.
I don't know the papers.
Yeah,
Thanks for the pointer.
Okay, someone has a very last question. Okay, then let's thank the speaker.